Dryden Lecture in Research. My name is John Chryssidis, the chair of the AIAA Dryden Lecture Awards Committee and a member of the AIAA Honors and Awards Committee. The Dryden Lectureship is one of the most prestigious lectureships bestowed by the Institute. Since the inaugural lecture in 1961, it has been the catalyst for sharing research advancements and knowledge. This premier lecture is named in honor of Dr. Hugh L. Dryden, a renowned aerospace leader and director of the National Advisory Committee for Aeronautics, as well as the first deputy administrator of NASA when the agency was created in 1958. The award emphasizes the importance of basic research in advancing aeronautics and astronautics. It is now my distinct pleasure and honor to introduce to you the winner of the 2023 AIAA Dryden Lecture in Research, Dr. Rodney B. Bowersox. Please allow me a bit to talk a little bit about his biography, describing his incredible career. Dr. Bowersox is educated and inspiring the next generation of aerospace engineers at Texas A&M University. There he serves as an Associate Dean for Research and the Ford I Professor of Aerospace Engineering. Last year, he was named a University Regents Professor, the highest honor bestowed by the Texas A&M University system on faculty members. Dr. Bowersox received his doctoral, master's, and bachelor's degrees in aerospace engineering from Virginia Polytech Institute and State Tech University. He founded and directs the Texas A&M University National Aerothermal Chemistry and Hypersonics Laboratory. Dr. Bowersox is a fellow of AIAA. He's also a fellow of the American Society of Mechanical Engineers, as well as a 2017 to 2022 DoD Vannevar Bush Faculty Fellow. His lecture today will address the national interest in hypersonic flight. Dr. Bowersox will share highlights from the recent hypersonic flight experiment from the Texas A&M University faculty and students that was managed by the Air Force Research Office of Scientific Research, and also included many Texas A&M faculty and students. The flight was successfully launched from NASA Wallops Flight Facility in March 2022 to further the understanding of drag and heating on hypersonic conditions. Dr. Bowersox will now speak on hypersonic wall-bounded viscous flow theory, ground, test, and flight. Now please join me in welcoming our distinguished lecturer to present the 2023 Dryden Lecture in Research, Dr. Rodney B. Bowersox.
John, thank you for that very nice, maybe embellished a little bit introduction. I do appreciate that. I'm just going to go to the next slide. I have too many slides for the time, but most of you that know me, that's sort of a standard when I give presentations. But I have a lot of people to thank for the award here. AIAA, not just for this award, but just for being AIAA. Thank you. I would love to list all the names. I don't have time for that, but the graduate students have been a mainstay of my career, and they're brilliant, and they're enthusiastic, and I love every one of them. My colleagues that I've worked with over the years have been generous with their thoughts. I've highlighted Joe Schetz. He was my advisor, and he's continued to be a mentor, and he's also very generous with his thoughts as well. And of course, the financial support by our sponsors, but equally important is the technical collaborations and the drive that they bring to all of the projects that have supported all of these people. And so the outline for the presentation, I keep wanting to look behind me, but I can't do that. The outline for the presentation, I've really broken it up into two pieces. The first piece will be an introduction, a little bit of motivation, background for hypersonic viscous flows, and then I'll talk about the Bolt 2 flight experiment. So the U.S. currently has a renewed interest in hypersonic flight. This is driven by national security interests as well as access to space. We're not starting from ground zero. We've been flying hypersonically for about 75 years. The first flight is this bumper whack 1949. And for the Aggies in the audience, that's Frank Molina, and you may recognize those boots that he's wearing. But we have a strong history in hypersonic flight. And an observation, maybe it's a hypothesis, is that these flight system development efforts required a synthesis of modeling, simulation, ground, and flight tests to be successful. And I've listed the Bolt flight test program at the top right there. Thermal management is another key challenge associated with hypersonic flight, and I chose the X-15 primarily as an example for two reasons. One, Hugh Dryden was instrumental in the X-15 program existing. And then secondly, we did some experiments at A&M where we tried to reproduce in our wind tunnel the thermal loading that resulted in the loss of that scramjet engine test article just below the X-15. And we were able to successfully reproduce that experiment. Moving on. My last motivation slide is really based on Air Force interest in hypersonic viscous flow. And the Air Force Research Laboratory has engaged in a number of flight tests, starting with the High-Fire 1 geometry, which is a 7-degree cone, bottom left there, HF1. That produced two-dimensional flow field, two-dimensional boundary layer instabilities. Moving to the right, the second geometry was a 2-to-1 elliptic cone, which produced a convex surface with three-dimensional instabilities and three-dimensional boundary layers that led to cross-flow breakdown to turbulence. And then finally, the bolt geometry, which is shown there, which is a concave surface with highly swept leading edges, which has some of the same features as the elliptic cone in terms of flow structure, but it is more dynamically rich in terms of the number of secondary flow structures set up by the shock structure. And we'll talk more about that as we move on. But heating is really important for hypersonic flight. And as we transition from laminar to turbulent flows, we can see anywhere from 5 to 10 times the heating level. And the skin friction follows suit via the Reynolds analogy. Okay. Just a little bit of background on boundary layer, hypersonic boundary layer viscous flows. And this may seem a little sophomorish, but I just wanted to take a minute and walk us through some of the processes because this will set the stage for the flight test experiment. I'm usually wanting to use the laser pointer, but you can't see that. But starting from the leading edge of this hypothetical vehicle along the bottom, you have a shock layer, and we'll go through each of these in more detail. But you have a shock layer and highly curved shock wave, which produces an entropy layer, which is basically a change in entropy as the shock is turning around and following the body. And that entropy layer leads to vorticity, which can impact the growth of the boundary layers and impact the receptivity in the boundary layers. And then eventually the boundary layer will reach a high enough Reynolds number and the disturbances will be such that the boundary layer will transition to turbulence. And then when that happens, you get an increase in heat transfer. And because hypersonic flows involve high temperatures, thermochemistry, radiation, gas dissociation, it's a very multidisciplinary, but that's what makes this problem very exciting, is it involves a lot of disciplines and you have to work these problems simultaneously or work together to make progress. So I'm going to walk through some of these regions really quickly. And so this is the leading edge region there. The blue section, looking at the figure with all the red and blue dots, that's the air molecules, or my sketch of the air molecules. The blue region there is the vehicle nose. The blue line is a boundary layer, and the shock wave is out in front. And as these molecules at very high Mach number go through this shock wave, they get excited, and you can introduce a region of thermal non-equilibrium where the translational temperature will jump very quickly. And for this example that I'm showing on the right with the Schlieren, that's a Mach 15 shot in our hypervelocity expansion tunnel. And just downstream of that shock wave, the temperature is about 12,000 degrees Kelvin. But then when we reach an equilibrium state just a few millimeters downstream of it, it's about 6,000 degrees Kelvin. So being able to compute all of that's really an important factor. And all of that's feeding into the boundary layer to influence transition, turbulence, erosion, ablation. All of those factors are happening in these flows. So let's move to the next slide. A little further downstream, we have the laminar boundary layer growth, and these boundary layers experience, or these hypersonic flow fields create highly curved shock waves, and these boundary layers will experience pressure gradients due to these shock waves because the boundary layers themselves will grow very rapidly. And that creates a displacement which changes the shock shape, which then ultimately changes the boundary layer. So it's a very coupled problem. It's a solved problem, though. This is not something we have. This is a laminar problem. We can solve this problem. So we've solved this problem for the Bolt 2 geometry. And I'm going to take this slide to introduce the Bolt 2 geometry in a little bit more detail. We're looking, the flow is going up the geometry there. The nose is at the bottom. And you can see all of these vortex streaks on that boundary. That's the laminar basic state. So this is a very complicated laminar flow. And each of these structures then provides a different mechanism, a potential mechanism to lead to transition from laminar to turbulent flow, as well as complex early turbulence. So trying to understand and decouple all of this is the purpose of the Bolt 2 flight experiment. So let's talk a little bit about boundary layer transition. And if you look at the red text, the red diagram on the right, what we're looking at the top of that where you see the forcing environment disturbances, that would correspond to the laminar flow. And you can see those disturbances that I've sketched there sort of propagating with the curved arrow. That's moving into the boundary layer. And the boundary layer will take some of these disturbances and amplify them. Some will be damped. It depends on the structure of the boundary layer, the velocity gradient, the temperature gradient, the pressure gradients. All of these things can have an influence on the boundary layer transition process. But once the receptivity process happens and these disturbances make it into the boundary layer, you start to see growth of some of these. And you have modal growth. That's along path A. And typically we're talking about first mode, which is Tolman-Schlichting. Second mode would be an acoustic mode, which only occurs at high Mach number. You have crossflow and Gertler. Those are crossflow is a three-dimensional boundary layer instability. Gertler is due to concave curvature. And there are other modes that maybe we haven't identified yet. And then there are other mechanisms listed. You have transient growth. You have bypass to the far right. And then the secondary mechanisms are mechanisms that result due to the distortion of the boundary layer due to the primary mode mechanisms. Prediction of transition for these types of problems really hinges on identifying the mechanisms and identifying when they're going to transition to transition. So the tools that we have under our belt to study this is direct numerical simulation of the Navier-Stokes equations, or we can use stability theory. And stability theory ultimately works its way into a eigenvalue problem. And we look at the growth rates, and at a certain growth rate, we'll determine we think transition may happen at this particular N factor. And the N factor is a measure of the amplitude at the location you're at, normalized by the initial amplitude, and that's typically, these scale exponentially, so we typically talk about these on a log scale. So let me just go to the next slide. So second mode, this is what it looks like, and these are some measurements from Farhan Siddiqui and Bill Sarek and myself in the Mach 6 quiet tunnel at Texas A&M. And you can see that rope-like structure in the boundary layer. I keep pointing down there, but you can see that rope-like structure in the boundary layer. That's the second mode instability, and you can see the growth rate of that second mode instability. You can see that peak around 300 kilohertz, and then you can see it break down to turbulence around 9.5 million per meter in terms of Reynolds number. Just keep that picture in your mind because that's going to be important when we talk about the Bolt 2 flight test. The other mechanism that's important for the Bolt 2 flight test is crossflow. And these are some measurements from Ian Neal, also in the Texas A&M Mach 6 quiet tunnel. And you can see a couple of things here. You can see on the figure on the left, which shows the color contour of the streak structure. Upstream of those red regions are vortices, which are called crossflow, stationary crossflow instability vortices that result due to the fact that you have flow wrapping up around the 2-to-1 elliptic cone and forming a sort of a mushroom region in the center there. And so you get a span-wise velocity gradient that results in these instabilities. And these lead to transition along these instabilities. And that jagged front that you see there is characteristic of crossflow instability. Below that is a numerical simulation from Helen Reed's group by Alex Moyes. And what that is showing is one of those crossflow vortices. And you can see that distorted boundary layer. So that results in a number of additional instabilities. And these instabilities are the secondary mechanisms that can also lead to boundary layer transition. And the power spectra that you see there in the middle, Ian measured that with one of the PCB transducers. He was able to pick up that secondary instability which led to breakdown to turbulence in those red streaks on this geometry. So again, this is another building block towards the Bolt 2 geometry. So on the Bolt 2 geometry, we have this complex laminar basic state with all of these vortex flow structures. And so the question then becomes, which of these structures leads to transition? And how long does that transition persist into the turbulent flow field? And so there's been a lot of work in preparation for this flight test. I'm showing some simulations. The laminar basic state was run by Brian Morali at Texas A&M. And then there's also some numerical simulations that were run for the Bolt 1 geometry, which is the same geometry as the Bolt 2 geometry, out of the University of Minnesota. And you can see second mode identified in these DNS simulations. You can also see a vortical mode, you can see mixed modes, you can see traveling cross flow, and so all of these modes that we just talked about earlier are present on this geometry. So when you see second mode, you can think about that rope structure that I showed you. When you see the stationary cross flow, you can think about the 2-to-1 elliptic cone. And the question is, which of these things leads to transition? So that's the transition part. So now we're going to move to the turbulent part of the flow field. And turbulence has a number of different characteristics, but the one that I'm going to focus on here is it's characterized by a wide range of scales, and this range of scales depends on Reynolds number. The higher the Reynolds number, the larger the range of scales. This is both temporally and spatially, so that makes numerical simulation a challenge. However, direct numerical simulation techniques do exist, and they are informing the community on the dynamics of turbulent flows, but they are limited to relatively modest Reynolds numbers, and when you bring in hypersonic effects, such as chemistry, thermal non-equilibrium, you introduce additional equations into the equation set, and that's at extensive computational cost, so it becomes even more challenging to do direct numerical simulations. Large eddy simulations exist. Large eddy simulations provide an opportunity to you simulate the largest scales and you model the smaller scales, so you can bring a little bit of the physics into the problem. Those are computationally feasible for some shapes, while modeled LES, and there's a table at the bottom there from Choi and Moyne, which lists the Reynolds numbers. So practical Reynolds numbers are 10 to the 7, 10 to the 8. So for DNS, we're talking 10 to the 15, 10 to the 18 mesh grid points in your mesh. Wall resolved LES, 10 to 9, 10 to 11, that's doable. Wall modeled LES, 10 to the 8, 10 to 9, that's definitely doable. The DNS ones are a bit more of a challenge for us, but we're making progress. And then Reynolds average Navier-Stokes is where we average out all of the fluctuations. These are the least accurate, but these are at least relevant for hypersonic design cycle. And I have a figure here, which is a PIV image from our laboratory from Ben English. Some of you that work with Sandia may know Ben English. This is a top-down view of a hypersonic turbulent boundary layer, very high Reynolds number Mach 5 boundary layer, and you can see the scale and the structure that we're talking about in these flow fields. So this is a beautiful image, and it's a challenge to resolve all of these physics. In terms of analysis for these flows, this is a little bit different than what we would do for the transitional problem, where we're trying to find the mechanism and identify where that breaks down. Here we're going to modify the conservation law equations. We're going to solve them directly for all of the turbulence, or we're going to modify them by doing a decomposition, a Favre or Reynolds average decomposition. And so you can think of that instantaneous velocity at the top there, U sub I, is equal to either the resolved plus the unresolved part, or the mean plus the fluctuating part. You substitute all of that back into the conservation law equations, and what happens is you introduce the closure problem for turbulence, which is shown here. So these moments in the box, the boxed expressions there, are new unknowns that we have to either resolve or model, and that becomes the challenge. And this problem's been around for about 120 years, so this is not a new problem, and there's some job security in working in turbulence, I think. And there's some great images by Nick Bissick from AFRL, where he basically studied the effect of poorly resolving. So he's got a well-resolved LES simulation, about 3.5 billion points, and then he starts to just systematically reduce the number of grid points, and around 60 million, he stopped there. You start to see significant differences and significant errors. Those can be traced to the subgrid modeling and all of that. So there's a lot of work to be done in turbulent flows. And where we are in terms of an industry standard, I've been to a number of talks today. Almost everyone runs the Spilot-Armorez model, or the K-Mbenga model, or Minter's SST models. And all of these models have one thing in common. They're basically computing an eddy viscosity, which is the mu-T and the expression on the right for the turbulent Reynolds shear stress. They have advantages. They have a strong low-speed basis, relatively simple to implement into a CFD code, because you just basically could have a subroutine, computes the eddy viscosity, you add that to the viscosity, now you have a turbulent flow solver. There's some challenges, though, for high-speed flows, and I'm just going to talk about a few of them, the top two there. Number one, the near-wall treatment, even at low-speed flows, is ad hoc and empirical. That's a challenge, and it's resulting in inaccuracies, especially at high speeds, at high Reynolds numbers, with cold walls. That's just a fact. And they can't capture strong favorable pressure gradients where we've observed that the Reynolds shear stress change is signed And so that's a challenge. So people have done different things. RANs beyond Boussinesq, which would be going to the second order transport equations. I'm not going to put a quiz at the end of this on the equations, but what I will do is talk about these equations. These are derived by taking moments of the Navier-Stokes equation, so this allows us to derive an evolution equation for the Reynolds shear stress, for the energy flux, all the different things that we need to do to model hypersonic flows. But the problem is that it introduces new unknowns, and so we have to draw models somewhere. So the question is it worth our while to do this? And so I have one set of data here that's the answer to that question is, of course, yes, or I wouldn't be talking about it. Of course, we want to do this. And this is just an example why. This is a 2D flow. The blue figure there in the middle is a 2D flow, Mach 5 over an adverse pressure gradient, a zero pressure gradient, and a favorable pressure gradient. And I'm going to draw your attention to the favorable pressure gradient results where I have the red circle on the right. And you can see the Reynolds shear stresses go to zero, and in fact, a little bit further downstream, they go negative. It's difficult to model that using a Boussinesq approximation. So the question is, does the Reynolds stress transport equation do a better job? And the answer is it does. I was able to prove that. There's the solid black lines are the Reynolds stress, the original Launder, Rees, and Rode version of the Reynolds stress transport equation, evaluated with experimental data, and it goes really right through the data for both the zero pressure gradient, the adverse pressure gradient. It misses a little bit near the nose region, and for the favorable pressure gradient, it gets the near wall region completely wrong. And that's expected because when you look at the physics of this problem, Scott Peltier went in and made measurements in our Mach 5 tunnel, and he demonstrated that the near wall structure is fundamentally altered by the favorable pressure gradient. So the modeling that we do for the zero pressure gradient flows certainly won't apply to the favorable pressure gradient case. And so we can trace that to this near wall term that's highlighted in yellow, and with an arbitrary change of that C7 constant, we're able to fix this for this particular problem. That doesn't make it a model, that's still a curve fit, but the point of this whole slide is to demonstrate that moving beyond Boussinesq will pay dividends. And so that's the importance of this slide. And this leads, and the goal for us is to extend these ideas to all of the moments that we need for hypersonic flows. So that leads to our laboratory. So we've developed a laboratory specifically to study these kinds of flow fields. And I'll just talk briefly about this. This laboratory houses 3 relatively large scale, I think important hypersonic wind tunnels, the Mach 6 quiet tunnel, which came to us from NASA Langley. And that came to us because we hired Bill Sarek and Helen Reed in 2005, so that was a gift from NASA Langley because we brought 2 of the leading experts in boundary layer transition to Texas A&M. The actively controlled expansion tunnel is a conventional tunnel that we designed and built in-house at Texas A&M. That's a workhorse facility. Those 2 facilities share infrastructure, and since they've been operational, since around 2010, we've run them about 5,600 times. And what we do is we increment the stream tube length for each run, and if you add them up over that 5,600 times, we've gone around the world 3.5 times at Mach 6 in these tunnels. So that's pretty impressive. We've generated a lot of data out of these facilities. The newest facility is the hypervelocity expansion tunnel, which is our high enthalpy facility. You've already seen a result from that. That was that Orion capsule. And this facility is a large-scale facility, has a 3-foot exit diameter, and we can do flight matched up to about Mach 15 or 5 kilometers per second. We can go faster than that, but that's flight matched with clean aerothermal chemistry. We can go higher than that, but we'll lose some of the aerothermal chemistry. We'll start to create issues in the flow field. Or we can go the other way, and we can run this at low temperatures and get exceedingly high Reynolds numbers. We can get over 100 million per meter Reynolds number in this same facility. So those are the 3 major facilities within in what we call the NAL. Our diagnostics, the NAL sits right next to what we call the Aerospace Laboratory for Lasers, Electromagnetics, and Optics, which is run by Dick Miles. It shares a wall, and all of the facilities now are surrounded by lasers from Dick's group. And I would say 1 in 5 experiments that we do, we're validating a laser diagnostic technique for the Alamo. And so we're really excited about that. In terms of computations, we're moving into doing direct numerical simulations in our laboratory. That's a heavier lift than we thought, but we're working our way through it. And we do a lot of reduced order modeling, as you've seen on the previous slides. And I want to talk a minute about this figure, even though it has nothing to do with Bolt. The top figure is a shock-shock interaction, creating a Mach stem standing in the free stream. So if you look at it with the naked eye in the photograph, you can see the bright light coming out of the window. That's what it looks like when we run the facility. If you look at it with a high-speed camera on the far right, I'm sorry, that figure was on the left. On the far right, that bright white light is what it looks like with a high-speed camera. And the big area in the middle there is what it looks like when you run it through a spectrometer. And we can pick up all the different electronic states that are being excited, the dissociation of all of the different species. And we can see what's going on there. This is spatially and temporally resolved optical emission spectroscopy. This was set up by Chris Limbach over a weekend. And so that's just a fantastic experiment that Tyler Dean is working on. And then, of course, Brian Morali has been doing the DNS calculations for what we call the ONR ogive. This is the blunt ONR ogive. And we're running these experiments also in HXT at very, very high Reynolds number. You're looking at me like I need to go faster. I'm doing okay on time. Fine. All right, so that brings us now to the Bolt 2 flight test, which is the boundary layer turbulence flight test in memory of Mike Holden. Mike was a co-PI on the project with Aaron Dufresne. So this project was out of A&M and with Kubrick. I was a PI, Helen Reed and Ed White were co-PIs from Texas A&M. Aaron Dufresne, Tim Wadhams, and Mike Holden were the PIs from Kubrick. We lost Mike in the first year of this program. That's a photograph of Mike with Bolt 1. And this plaque, which was written by his colleagues and his family, was mounted to the Bolt 2 geometry for the flight. And on there, they quote, higher and faster twice. I just want you to kind of keep that in mind as we move forward. But a lot of the force behind how we operated and set up the Bolt 2 flight test program was driven by Mike as we were writing the proposal. And so the Bolt 2 flight test team, there's a lot of people on this slide. Every one of them contributed to the success of the Bolt 2 flight test. And I'll start with the top box going from right to left. I'll start with Yvette Leyva. Having a university lead a flight test program was her idea. The Bolt 2 geometry, the concave curvature with a highly swept leading edge, her idea. Without her, this program doesn't exist. She left AFOSR in the middle of this, and so Brett Pequenes took over, and he did a fantastic job of keeping us on track until Sarah Popkin was hired. And Sarah Popkin came to us from the Johns Hopkins Applied Physics Lab with a lot of flight test experience. And without that line across the top there, the flight test wouldn't have happened, without question. The second line, Dave Abenzak, National Treasure, Nick Bissick, Doug Dalvin, Roger Kimmel, that whole group. Without the Air Force Research Laboratory participating, again, I don't think we have a successful flight test. And so then the science mission was led by TAMU and Kubrick. The payload system was led by AFRL. The flight system along the bottom there was provided by NASA Wallops and the NASROC team there. And then there was a whole host of supporting ground test experiments and ground test computations by all the folks listed on that chart. And we want to acknowledge this. I want to acknowledge here the funding from AFOSR, AFRL, OUSD, and Lockheed Martin. All of those folks contributed to the funding of this flight test program. And so what were our objectives? Our objectives were to create a database to quantify natural and forced turbulence during hypersonic flight. We also wanted to directly assess the ability of ground test and simulation to extrapolate to flight. And in particular, this is where Mike Holden really was insistent, is we were going to test, and we did do it, the actual flight hardware in the Kubrick Lens 2 facility with the actual flight instrumentation before we flew it. So we did those experiments, and that happened. And then, of course, numerical simulations, DNS out of University of Minnesota, University of Maryland, University of Arizona, stability calculations out of Texas A&M, RANDs out of everywhere. And then the third goal for this project was to promote external engagement workforce development. So in terms of this program, there were 20 organizations that were participating with about 40 subject matter experts, and we also supported about 10 graduate students through this program. And I'll talk a little bit more about that particular element as we go along. And this bottom line along the bottom here, this was insistent from AFRL and specifically Roger Kimmel. Bolt 2 is to serve as a scientific benchmark for hypersonic heating, and we did that. Just to go through the geometry in a little bit more detail before I go to the next slide, It was a symmetric shape. It looks a bit like a shovel there. We have highly swept leading edges. The radius of curvature, or not the radius of curvature, but the radius of the leading edge was a 0.5 millimeter, so it's relatively sharp. And it created a complicated shock structure and a complicated interaction with the boundary, produced all of these streak vortices. The vortices are everywhere on there. And so side A was the side that we focused on, which it was natural transition. NASA Langley, Scott Berry focused on slide B, where he put some trips on the side to look at forced transition on this geometry. So there were 2 experiments that took place during this flight test. Okay? So what were our questions? So what I'm showing here is sort of the bottom line up front, sort of image. So this video on the left is the Bolt 2 geometry, or an elongated version of the Bolt 2 geometry in the Mach 6 quiet tunnel at A&M, the one you just saw. And you can see that streak structure that we see in the laminar simulations, and then you can see breakdown to turbulence happening where it turns yellow. When you put that in the ACE tunnel, it looks different. The ACE tunnel is a conventional tunnel, so you end up with a different kind of response. So the question that we ask is, well, what is the mechanism that leads to turbulence in flight? And how long, once we determine that, how long do these processes persist into the turbulence? And then what is the role of non-uniform temperatures and pressures? And I want to point out that we also did these PSD measurements, very much like we did for the 2-to-1 elliptic cone. And you can see this secondary instability on the PSD just below that figure, lighting up around 200 kilohertz. The right image is the DNS out of Graham Candler's group, and you can see again that secondary instability lighting up around 200 kilohertz. So there was great agreement between the experiment and the direct numerical simulation. Okay, so this is the project execution, and I wanted to start this with this quote from Hugh Dryden, bring him back into the picture again. The purpose of flight research is to separate the real from the imagined and to make known the overlooked and unexpected. I can tell you there was a lot of things that were unexpected when we set out to do this flight experiment. One of them was the number of reviews we had to go through. We went through, at the top line are all the Air Force reviews. We had the conceptual design review, the preliminary design review, the critical design review, the technology review board. Then we had the NASA reviews at the bottom, which is the mission initiation review, the readiness review, the design review, the mission readiness review. We were reviewed all the time. In fact, I counted it up. I went into Google Calendar and counted up how many meetings we had associated with the Bolt 2 flight test. It was 250. Over 250 meetings associated with this flight test. This was an enormous task that we worked through. So step 1 was to design the flight experiment. We did all of that. Step 2 was to build the hardware. That was the Kubrick role on this. And of course, Aaron DeFreem was instrumental in designing the flight experiment as well. And then performed the flight experiment, which took place on March 21st, 2022. And we're currently analyzing the data. There's a lot of it's being released at this conference. There's been 3 sessions today on the Bolt 2 flight program. There'll be another session tomorrow where we'll start to release some of the flight data. But before we talk about the flight data, I want to talk about one of the ground test experiments that Heather Kostak did in support of this. And so we had a subscale model, 25% subscale models that we put into the Mach 6 quiet tunnel. We did IR thermography, PCBs, cool lights, hot wire anemometry. And I'll just cut to the chase on this because I will run out of time. So what she was able to do was quantify the breakdown mechanism, at least under quiet flow in our wind tunnel. And what she identified is that mixed mode structure that we saw earlier in the DNS calculations from Graham's group. And you can see it again here. I keep wanting to point with my laser pointer, but I can't do that. You can see that those bright stripes on the experimental images in the black and white aligning with sort of that similar region on the DNS calculation. That's the mixed mode region. So she went in with hot wire anemometry and measured that breakdown and did off-body measurements. And you can see the mean flow measurements on the left. The DNS is at the top. The measurements are at the bottom. You can see great agreement, great qualitative agreement. The hot wires weren't calibrated. And then if you look at the fluctuations, you can see also really good agreement between the DNS fluctuations. And those bright red spots there our secondary instability modes growing and wanting to break down. So on that Morkovan figure where we had the secondary instabilities, that's what you're seeing in those bright red spots on both the DNS and in the experiment. And the bottom image, she started to look at a specific frequency band to pull out, looking for a specific mode. So that's really interesting results, and that actually will help interpret what we see in the flight test data. And so with that example, we did a lot of things to design the flight experiment, and you can see on this figure a laminar solution, a second mode stability calculation out of Helen Reed's group, cross-flow stability calculation out of Helen Reed's group, ACE tunnel experiments out of our group, and then the turbulent calculations. And then on the far right, you can see the instrumentation layout out of Brad Wheaton for the Bolt 1 flight test. Okay, so let me talk about this instrumentation layout and why we did what we did. So what we did was we leveraged all of these ground test results to design the flight experiment, and so we laid out the instrumentation. But the other factor that came into this, and the reason this looks the way it does, was because of the preliminary design review. And Roger Kimmel, Brad Wheaton, and John Lafferty all asked the exact same question. How are you going to tell the difference if this thing is coning in between those streaks sweeping back and forth and turbulence on this? So that fundamentally changed how we had to think about the instrumentation layout. So let me just walk our way through the rows here, and we'll talk about what I mean by that. So the first row at the top, we have a nickel nose and a stainless steel frustrum. I'll talk about that on the next slide. So that first row of thermocouples there, and those are the MedTherm thermocouples that you see at the top on the box on the right. That first row was there to measure the temperature along that interface so that we can quantify any steps that may happen because there's differential thermal coefficients of expansion. There's also a pressure transducer circled by the pink circle. That's to understand the attitude of this model. Is it pitching, is it pitching or yawing? So we have pressure transducers to help us understand that. We have similar pressure transducers on the back side. The second row up there near the leading edge was specifically to quantify the streak location. So we have a high density of instruments across there to quantify the streak location as they may be sweeping back and forth. So that's sort of the inflow condition to the turbulence at the bottom. And the rows 3 through 5 were set up to quantify that transition front and the turbulence as this thing is descending into the atmosphere and the Reynolds number is going up. That transition front is going to move forward. All those mechanisms that we talk about are going to move forward, and eventually this is going to go fully turbulent. And so all of these transducers, all these instruments on the bottom were designed to quantify all of those. And so I'll run down the list. We've got the pressure transducers. We also have Kubrick thin film sensors to measure the turbulent bursting. On the left, you can see 4 PCB sensors that were put on there to measure the turbulent spectra. And these are high frequencies. These were sampled at 2 megahertz. And then because we can't telemetry back 2 megahertz of data, what we ended up doing, and this was Dave Adamczak, is we onboard did FFTs, and then we telemetry down the top 20 FFT peaks every 9.2 milliseconds. And you'll see some of that data in just a few minutes. The Vattel thermogauges are there to directly measure the heat flux. And then we have the ohmic skin friction gauges from Ryan Merritt there. You can see all of those. And then some of these instruments we clustered in a way to allow us to infer Reynolds analogy along with the surrounding pressure field on this as well as the temperature field. And I should point out that the MedTherm thermocouple temperature was measuring the temperature on the outside surface and the inside surface of the frustrum. So we used that to compute heat transfer as well. So there's about 300 sensors, about 400 channels of data coming out of this flight. In terms of flight stability, I don't want to go into the details here, but it took us about 9 months to come up with a stable flight for this geometry. And this is it. And one of the challenges with this geometry is it's an asymmetric leading edge, so the nose itself, the bolt geometry itself is a lifting body when you get a bit of an angle of attack. And producing a flight stable system was a challenge. We flew on the Terrier improved Malamute. The materials that were chosen for this was based on this flight stability and the fact that our Mach numbers weren't going to be so high. So we chose a nickel nose with a 410 stainless steel frustrum, and that was actually Aaron Dufresne. The other big advantage of choosing these materials, it's like a flying wind tunnel model, and so we get great signal to noise out of our thermocouples. So this was a great decision for this. And you can see the instruments on this, and you can see that cork board on there is thermal protection for the aluminum fairing to keep that intact. Before we flew, I'm running out of time, so I'm speaking a little faster. I apologize for that. I see John over to my right. So, but before we flew, and I've only got a few more slides. Before we flew, though, we did test this in the Kubrick Lens 2 facility at Mach 5.3. We chose 5.3 because our initial calculations suggested that our peak Mach numbers were going to be around 5.5. And so Aaron and company chose Mach 3 or 5.3 to do the experiments. 3 different Reynolds numbers. That's just an example set of data. A lot of that data will be released tomorrow. That's Heather Kostak and Tyler Dean out there for those experiments working with Aaron and his team. In addition to the actual flight hardware, AFOSR brought the MURI team, the High Flight's MURI team over to measure the atmospheric disturbances and the atmospheric conditions, as well as a ground-based HALIS group to measure atmospheric disturbances as well. And this is the team there. You can see Sarah Popkin dead center in the middle there. That's it. So let me just play the video. And this video, just to give you a heads up, was taken by Brian Morali with his cell phone. And so it's a great video, though. It's the best one we have. And you'll see people looking up. Everybody's looking up. And there goes the second stage. So let me show you what that did. So this is the measured flight trajectory for this. The dashed lines are the descent, and the solid lines are the ascent. So we flew to about 200 kilometers, and you can see we hit Mach 6, above Mach 6 on the way up, and we were very constant at Mach 6 on the way down. We hit Reynolds numbers up to 45 million before the fins. Actually, the thermal protection failed on the fins on the way back in. Second stage stayed attached the entire time. You can see that our angle of attack and our yaw angles were very small, so this thing came in really true. And Dave Kilcoyne, who did all of the stability calculations, came up to me and he goes, "Rodney, I'm really sorry." I said, "For what?" He goes, "We went too high and we went too fast." And I'm like, that's okay. And Tim Wadhams was there, and Tim Wadhams looks at Dave and looks at me and goes, "I think that was Mike, higher and faster." So it was a great experience, But the data, let's just look at some data just to give you an idea how good this is. So this box in the pink shows just an example pressure trace from that sensor that it's pointing to, comparing side A to side B. This is the descent flight trajectory, and you can see side A and side. This thing was coming in straight, not at an angle of attack. And I'll show you what the angles of attack are in just a few minutes. The black box to the right, which are some of the skin friction gauges there in row 5, you can see that the green one, which is the third one from the right, transitioned first, followed by the blue one, which is next to it on the right, followed by the blue one, the dark blue one, which is next to it on the left, followed by the red one, which is closest to the center. That agrees exactly with what we saw in the quiet tunnel. That process agrees with exactly what we saw in the quiet tunnel. And if you look at the heat flux sensors in the green on the bottom gold box pointing to the heat flux sensors, which are just upstream of it, you see the same thing. So just to make sure everyone understands what transition is, before 402 seconds there on the skin friction trace, you see that low value of skin friction. That's laminar flow. You can see some oscillations, and you can see the turbulent flow kick in, and it's increasing because we're diving into the atmosphere. So the Reynolds number is going up as we're diving into the atmosphere. The PCB sensors on the left, those green PCB sensors on the left, these show modal growth, and I've chosen 403.2 seconds, which is in the middle of that transition process. If you look at sensor 1, which is out on the far left, you can see about 800 kilohertz in terms of that modal frequency. That's probably a second mode we learned today. That's a second mode modal instability, probably showing up out there on the wing. That 400 kilohertz in sensor 4, which is one of the two close dots there in the middle. It's the second one in that middle. there, slightly downstream. That shows about a 400 kilohertz. That's secondary instability showing up there in that mixed mode region. And then that sensor 3 is closer to the center line. That's a second mode like instability in that center line region. So you remember those figures that I showed you earlier, which showed the rope-like structures and then the cross-flow type structures? Well, you're seeing that in this data. Okay, this is real time. This video is real time. So you're going to watch the PCB transducers on the left, and you're going to also watch the heating on the right. And this is John Worth's work. He's a PhD student working on this. This is a full 3D conjugate heat transfer analysis where he took the MedTherm data as the boundary conditions and solved the heat transfer problem for the steel frustrum to produce this video. So this shows laminar flow. Then you're starting to see some instabilities go, and then it's starting to go turbulent on those streaks, and you can see you have turbulent on that bottom wedge. This is real time, by the way. I can't play it again. I don't have that control. Well, maybe I do. I'll play it one more time just to show. I want you to watch the alpha and beta. This thing is coming in true. This is really great. It was a great flight test. This is just a little bit of the data. So every one of those instruments is an experiment. Each row of instruments is an experiment, and then collectively that data is an experiment. So there's just a lot of richness in this database, and we're going to be reducing data for the next couple of years on this. And then finally, tracking the transition mechanism. I won't go into a lot of detail here because I do want to leave time for a few questions, but you can see that the transition, this on descent, you can see that red line. That shows which transducer and which row transitioned first. So you can track the transition path, and again, it aligns. It's in great alignment with what we saw in the quiet tunnel. And we did see on the leading edge, transition on the leading edge at much higher Reynolds numbers. I will also point out that the REX for each of those sensors was roughly between 4 and 5 million per meter in terms of Reynolds number. In the quiet tunnel, we were measuring about 3.7, 4 million on the reduced scale model. And the reduced scale model wasn't exactly the same. It had a longer fetch. It was a 1.35 meter scale model, not the 1 meter model. So some of that difference may be there, but that's excellent agreement. So this is my last slide. I think this Bolt 2 flight experiment is a terrific example of modeling, simulation, ground test, and flight experiment working together to advance our basic knowledge of hypersonic viscous flows, and in particular, transition and turbulence over a concave geometry with swept leading edges. We've provided a new database for flight. We've provided lots of databases from wind tunnel experiments, as well as numerical databases coming out of the University of Minnesota and others. We're inspiring, I think, new modeling and simulation and ground test internationally. There's a group in Australia doing experiments on these exact geometries. And we're informing the next flight, which is the Bolt 1B. And I'm going to end with the quote from Sarah Popkin, which I've heard at least twice now, maybe 3 times, that this Bolt 2 flight test experiment exceeded all expectations. And so that's it. Thank you.
Thanks, Ron. Good job. Well, thank you, Rodney, for a very interesting lecture. And we do have some time for questions. I see that I don't have any on my iPad here, but if anybody wants to shout them out, shout them out. Any questions? It's got a couple. Well, one big one. How long was your longest test in the wind tunnel?
How long was the longest test in the quiet tunnel?
In every tunnel.
So the quiet tunnel runs for about 40 seconds, and then the shock tunnels run for order milliseconds. So I think the Kubrick facility was running about 15 milliseconds for the ground test experiments of the flight hardware. But and Tim Wadhams is there, can correct me, but I think it's about 15 milliseconds for Lens 2, 50 milliseconds in Lens 2, 40 seconds in the quiet tunnel.
Wow.
We did see transition on the leading edge, around 12 to 15 million in terms of length Reynolds number along the body. So we did. We didn't see it in ground tests, but we saw it in flight. We did. We couldn't go to those Reynolds numbers under quiet conditions in the flight. It was simply that, yeah.
So great talk. So other than the hours of being in all the design reviews, what would you do differently for the next flight that might come
That's a great question. Not a whole lot, actually. I think the flight test itself, the experience, I'm only joking about those. I loved every one of those meetings. It was fantastic. Future sponsor may be in the audience. But actually, for me, I think Basel, if I had things to do over again, I would probably change up some of the instrumentation suite. There are some instruments that we have learned worked much better in flight than other ones. And so just from a practical perspective, I think that knowledge that we have now about it would be invaluable. And we're feeding that knowledge into the next flight. So we're working with Brad Wheaton on his flight, giving him the best advice we can based on what we've learned. But in terms of this, doing it in a pandemic was hard. Because we did all of this during the pandemic, we had supply chain issues, all of that kind of stuff. That actually influenced a lot of the instrumentation choices we had to deal with. Also affected how we did our preliminary design review and how we did our conceptual design review and our critical design review. All those had to be virtual. So doing the design reviews virtually, I don't recommend that. So hopefully, if we ever get to do this again, and I hope we do, it won't be during a pandemic, so we can do things in person. I think there was a lot of things that were lost doing it virtually.
Some questions are coming in, actually. Any concerns with the transducers inadvertently transitioning the boundary layer?
Great question. That was actually an RFI question we got as well. Do we need to contour the sensors? The bolt geometry was actually very mildly curved. And so for the sensor diameters that we had, there were really no significant steps. So we weren't worried about steps transitioning those. The other question would be hot spots due to the fact you could have a thermal mismatch. The med therms matched up perfectly, and we placed all of the transducers far enough apart so that we wouldn't influence one transducer by another transducer's hotspot, but there were going to be some hotspots that show up in the geometry. But we didn't really worry so much about those changing the transition mechanism.
Okay.
There's a question there also.
Oh, go ahead.
This was a really inspiring talk for those of us who love elaborate and interdisciplinary experiments. I really love the talk. I have a question. Is there any role for optical diagnostics in this kind of work?
Can you repeat the question for me?
Yeah, so the question was, is there any role for optical diagnostics in this kind of work? And I think, I saw Dick Miles right behind you. He would be a better person to answer that question. But yeah, I think the answer is absolutely yes. Both in ground test, and I think if we can be creative, we could probably even do something in a flight test. And we could talk offline about what I'm talking about there. But absolutely, I'd love to talk to you about that, Andrew. That would be good.
So another question is, what are the most significant boundaries to applying these prediction methods to vehicle design, besides the computational time?
Great question. So it depends on which part of the problem that you're looking at. So if it's the transition problem, I think the biggest challenge, and I think we're getting through this, is identifying which mechanisms. There's a whole host of mechanisms that can lead to transition. So let's just say you have a fin, or you have some others creating a separated flow field with vortices and pressure gradients. Having confidence that we can simulate those accurately is still something we're lacking. And I think, so more ground tests to prove that we're simulating these properly, more flight tests to prove that we're simulating these properly. So the transition problem, identifying the mechanisms. And then for turbulence, the turbulence problem is the closure problem. And as we go to hypersonic speeds and we take turbulence models that were designed, calibrated for low-speed flows, and then apply them to high-speed flows and try to correct them, I think in some sense may not be the best strategy. I think we should probably just start with a clean sheet of paper and work our way through that, because some of the, you can point to lots of different problems, modeling dissipation. If you look at the equation for dissipation, it's simply made up. And so it doesn't work well. And so there's just a lot of work to be done there. So turbulence modeling, thermochemistry, transition, coupling it all together, those are all just really hard problems. I mean, if there were easy problems, we would, but those are the barriers. Those are the barriers.
Great. So another question here is, why go back to bolt one? Why not try new geometry that was more complex?
Good question. And that's not a question for me. That would be a question for Sarah Popkin. But I think the idea there is the bolt one instrumentation suite was different, and it was really there to give a much clearer and cleaner picture. We were fortunate that we picked up some of the modes in transition, but what we'd really like to do is look at the evolution of the transition process. And so the instrumentation suite that we had didn't do that. So I think the big deal would be the instrumentation suite, and I think Bolt 2 or Bolt 1B is going to go to a higher Mach number than Bolt 1A was planned to do. So.
Okay, we'll end with a very specific question. For programs that are not yet in flight test phase, but may get there one day, what can we do now to set ourselves to success later? Very specific, I know.
Let me think about that for a second. I have so many answers, and some of them will seem a little tongue-in-cheek. When we first set out to do the Bolt 2 flight test, and we went to the NASA Mission Initiation Conference, I was pretty confident that I was ready for that meeting, but I was not ready for that meeting. So what they handed me was the Sounding Rocketry Handbook, which is about 150 pages, and so I went back and I read the Sounding Rocketry Handbook. So I would read the Sounding Rocketry Handbook if you're going to do a flight test, and that's available at NASA Wallops. Understanding your question, I think also talking to people that have done flight tests. Having Roger Kimmel really be very critical of what we were doing made us a better flight test. So take the criticism with the way it's meant to be, which is to make you do a better job at what you're supposed to be doing. That was great. The questions from Brad Wheaton, who had just gone through this whole design process that we were starting up, it all came from a spot of trying to be helpful, but they were hard questions and we had to answer them. So just being prepared for those types of things is really kind of important.
Well, thank you again. Great talk, right? On behalf of AIAA and the Honors and Awards Committee, it is my privilege to present to you the 2023 Dryden Lectureship in Research Certificate and Medal. Oops. Can be without dropping something. Yes?
That wasn't the medal.
That wasn't the medal, no. Congratulations, Tom. Thank you, everybody. Have a great evening.